Okay. Hello everyone. So I can tell it's still midterm season. There's 2 of me and only 3 of you. So this is going to be more just in general for the recording purposes, so people can watch it later. But of course, I'm gonna if you guys have any questions, then I'm also here for that. But if there are none, we can get started. So welcome back to your Comp 335 tutorial. This is your 7th tutorial. In this tutorial, we're going to be continuing to look at context-free grammars, and specifically, if you're given a context-free grammar G, you want to somehow simplify your context-free grammar. And we're going to see in a minute what we mean by simplification. And once we simplify the context-free grammar G, then we can look at something that's called a normal form. So I realize for everyone here, this probably isn't something that you've covered in the lecture already. You're going to cover this tomorrow and this week. So this is going to be because the Monday section because the tutorial section is before the lecture. This is kind of going to be like a sneak peek to what you're going to see in the actual lecture. But hopefully it'll be also useful. So yeah, we're going to finish off with normal forms. But you're going to see that this part of the course is actually not as hard or as difficult as the other parts. Okay, so production simplification. The first terms that we're going to look at and the first parts of the grammar that we're going to want to simplify are going to have to do with lambda productions. So what is a lambda production? Just to remind you, a lambda production is essentially when you have a variable on the left-hand side and you have an empty string or lambda on the right-hand side. Okay, and then from that lambda production definition, we can derive another definition, which is of a nullable variable. So what is a nullable variable? It's any variable A such that you can get through one or more production rules, derivation rules, you can get your empty string. So for instance, if I have A gives me lambda, then of course A is nullable. But if I have A gives me B, or sorry, not A gives me B, if I have B gives me A, then B is also a nullable variable since you can go from B to A and then from A to lambda. Okay, so the whole idea behind this lambda production and nullable variable is we're going to want to get rid of these lambda productions. And the whole reason why we're doing all the simplification is going to be a lot clearer at the end of the tutorial. Okay, so how do we remove lambda productions and nullable variables? So suppose you're given this grammar G, where we're going to assume, just for the sake of simplicity, that the empty string does not belong to the language generated by G. Okay, so in other words, we're saying that the language that's generated by G is not going to give you lambda, and that's sort of the reason why we're doing this is because we don't want to sort of remove all the lambda productions and then say, oh, well, we lost the production rule that gave us lambda. So we're just going to use this assumption to make our life a bit easier, okay? And so given that grammar G, we can convert it to an equivalent grammar. So it's important that the grammars before and after the simplification are equivalent, meaning that they generate the same language. So we can get an equivalent grammar G prime with no lambda productions and no nullable variables by doing the following steps. So the first step is going to be, you're going to want to identify all the nullable variables. So as I said, all of the variables that you can get the lambda production from. Then for each production rule P, that's going to look like A gives you some stuff. You're going to just add each of these production rules to your new grammar, G prime. So essentially, you're going to add everything except the lambda productions. And then once you get to sort of adding all of the non-lambda productions, your grammar G prime, essentially what you're going to do is you're just going to replace every possible instance of the nullable variables by lambdas. So I'm sure that doesn't make any sense right now, but it will with an example. So that's what we're going to do. Okay, so we're given this following example. We have a grammar G with these production rules, and we want to eliminate all the lambda productions and all the nullable, all the lambda productions. Okay, so how are we going to do this? Well, remember the first thing is we're going to want to identify the lambda productions and the nullable variables. So what are they? Well, clearly I know that A gives me lambda. So this guy is a nullable variable. Then I know that C gives me lambda. So this guy is a nullable variable. Is there anything else? Yes. So I know that B gives me C, but then I know that C gives me lambda. So that means that B is also a nullable variable. Okay, so just to make sure that everyone's on the same page, again, a nullable variable, A. So if A is a variable, then it's nullable if you can, through one or more derivation rules, get to the lambda production, get to an empty string. And then Jenna, what brings you to lambda? I feel like you were answering a question. But yes, so, you were answering his, okay. Oh, whoops, sorry, okay. Sorry, I'm a bit slow today. All right, so you identified these guys, the A, C, B, so we know those are, yes, so A, B, and C are nullable variables, right? So because B gives you C and C gives you lambda. Okay, so then what we're gonna do now is we're gonna essentially copy all of this grammar here, except we're going to exclude this lambda production and this lambda production. So what are we going to have? If I copy paste this, and this, I'm going to have this, and this, okay? And then what I'm going to do, I'm going to say that for every possible combination of lambdas and variables, I'm going to add that to my production rule. So what I mean by that is here I have A, B, C, right? So either I can replace A with lambda, right? So if I replace A with lambda, I'm going to get A, B, C. So just think of this as being A, lambda, B, C, okay? Or I can replace C with lambda. So this is where I replace C with lambda. That's A, B, lambda. So essentially I'm just doing all of the possible combinations of replacing a variable by lambda or not, okay? So it's kind of like you're doing all the possible subsets. Then the same thing for AC. In this case, I'm doing A lambda C. So in other words, I replace this B here, the variable B here, by lambda. Okay, and then so that was for replacing a single variable by lambda. Then I can do it for two variables. So here I'm replacing B and C by lambda, right? And then here I'm replacing A and C by lambda, and here I'm replacing A and B by lambda, right? So that's for two variables. And then if I want to replace all of these guys by lambda, then I just replace A, B, and C by lambda. So that's why I just get an A. Okay, so the whole point here is I'm accounting for the lambda production by considering all the possible combinations of if I were to actually use that lambda production. Okay, so then again, the same thing for A gives you BC. Both of these are nullable variables. So in other words, that means that I can replace B by lambda, C by lambda. So this is replacing C by lambda, and this is replacing B by lambda. But so of course you have to be careful. You don't want to replace both B and C by lambda, because if you did that, then you would get lambda, lambda, and you would get back a lambda production, and the whole reason for this process was you wanted to eliminate these. So the main sort of tip here is to be careful that if you have only a sequence of variables like this, make sure you don't add the lambda production rule again, okay? And so once you're done replacing, doing all these replacements of lambda productions and nullable variables, you get this equivalent grammar G prime, meaning it's equivalent in the sense that L of G is equal to L of G prime, okay? And it has no lambda productions or nullable variables. So that's the whole point. That was the reason why we were doing this. And again, right now this seems really pointless, but you're going to see at the end when we look at normal forms, you need to get rid of lambda productions to get a normal form. Okay, so just to make sure that's clear, let's do an exercise. So I don't expect this to be super difficult. So I'll give you maybe like 30, 45 seconds as usual. And we'll look at the solution to that together. All right, so hopefully you had some time to start the question. Let's go over the solution. So again, here we're given a grammar G, and the idea is we want to convert it to an equivalent grammar G prime, where you have no lambda productions, right, and nullable variables. So what's the first step? The first step is to identify all the nullable variables and lambda productions. So what are they in this case? Well, I know that A gives me lambda, and I know that B gives me lambda. So that's my initial pass, and that's it, right? Because S, so there's a terminal here, so it's not going to give me lambda, and there's a terminal here, so it's not going to give me lambda. So these are my only which ones here? These are my only nullable variables, right? Okay, so again, once you do that, then what do you do? Well, essentially you just copy the non-lambda production. So you copy all of this and you copy all of this. So you get G prime as S gives you AB and AAB. So that sounds exactly the same. And then B gives you BB A, right? Okay, so that's step two. Step two is just essentially copy paste everything that's not lambda, right? And what's the third step? The third step is you're going to want to replace for each nullable variable. You're going to want to take all the possible combinations, right? So let's do it. So let me separate these. Let's do it for capital A, little a, capital B. So what are the possible replacements? Well, you can replace A, so capital A by lambda, so that would give you AB. You can replace capital B by lambda, that would give you AA. And you can replace both by lambda. In this case, you're not going to get a lambda again. So you can replace both by lambda and just get little a, right? And then the same thing for A2B. In this case, the only thing I can do is replace capital B by lambda, so I'm going to get AA, right? And then the same thing for this guy here. The only thing I can do is replace capital A by lambda, so that's what I'm going to do. I'm going to get BB. Okay, so maybe a question for you guys. What is there something kind of off about this grammar? I mean, clearly, if I'm asking, right? Okay. Well, so not exactly. The thing that I was thinking of is, in this case, A is actually pretty useless, right? You can use this production rule, but you're never going to get rid of the variable A. So actually, if you want to simplify it even more, what you could do is you could say, okay, well, I don't care about this one, and I don't care about this one, and I don't care about this one, right? So then you would get an even simpler grammar, which would just be composed of the terminal strings plus, in this case, the variable b, okay? And that should, yes, and so that's what we have here. So that's why if some of you looked ahead and saw that there wasn't a capital A, that was just because the variable A wasn't actually useful. It wasn't doing anything, okay? And we're gonna see a direct way of eliminating it in a few slides, okay? So I hope that's clear for everyone. As usual, you can stop me if it's not. But if it is, we're going to move on to the second simplification procedure, which is removing unit productions. So what is a unit production, first of all? A unit production is any production of the form a single variable on the left gives you a single variable on the right, okay? And these are not super useful in a grammar because essentially you can just replace everything that, so essentially you can replace this production by everything that B gives you, right? So that's going to be the idea. That's the idea behind this procedure, is you just want to replace it by everything that B gives you, okay? So we have this procedure here that if you're given a grammar G with some unit productions, then you can convert it to an equivalent grammar G prime. So again, the languages generated are the same, where you have no unit productions, okay? So how are you going to do this? Well, again, there's a step-by-step procedure that you can follow. The first thing you're going to want to do is you're going to want to remove any of the productions that are any self-production rows, right? Because these are clearly completely useless, right? They don't really add any information to the derivation, to your grammar, okay? The second thing you do is you want to find all of the variables, all the pairs of variables such that A through a sequence of derivations gives you B, okay? So for instance, if I have A gives me B, well, this is one pair. If I have also A gives me C, this is another pair. And something to be careful of is if I have something like B gives me D, then yes, I have B gives me D as another pair, but I also have A gives me B gives me D. So this is another sort of pair of unit productions, okay? So this should be a D. Yes, D, okay. So what was I? Yes, so you identify all of those pairs, and then you put all of the production roles that do not have any unit productions in your new grammar G prime, or in your new set of production roles P prime, okay? And then what you do is that for every, so if you have a pair A gives you B, right? In your initial step one, then, so this is in the production role P. If you're in the production role P prime, then essentially what you're going to do is A is going to give you everything that B gives you that's actually useful. So in this case, if I have B gives me x1 to xn, whatever x1 to xn are, then I would say A gives me x1 to xn. Okay, so it's pretty straightforward. You're just replacing it by what it's giving you essentially. Okay, so let's do an example just to make sure it's clear. So again, we're given this grammar G here, and we want to find an equivalent grammar G prime such that there are no unit productions. So what are the possible unit productions here, or what are the possible pairs of unit variables or productions? Well, first of all, we can look at the kind of obvious ones. So there's S gives you A, S gives you C, and there's also A gives you C, and there's also C gives you B, right? So these are the sort of first sort of super obvious ones, right? I hope I'm not missing any. No, it doesn't look like it. Okay. So then after you identify those, then you can sort of use the transitive argument that, for instance, S gives you C, right? S gives you C and C gives you B. So I also have S gives you B. And I also have that A gives you C and C gives you B. So A gives you B, right? Okay. So I've identified all of the pairs, and that's it. Yeah, it doesn't look like there are any more. Again, if you want to sort of do this, you can it's kind of like you do it for a first pass, and then you do it for a second pass. If you continue as long as there's new productions. If there aren't any new kind of discoveries or pairs, then you can just stop. Okay. So these are all the kind of pairs that have unit productions. So that's step. Well, I kind of skipped step 0. That's just because there are no self-productions. So this would be step 1. The second step is you're going to want to copy. Remember, you're going to want to copy all of the non-unit productions and paste them into your new grammar G prime. So in this case, S gives you, I'm not going to paste A or C, I'm just going to paste this. So S gives you BBB. A gives you A and BC. B gives you B, and C gives you these two guys, right? So we're going to need to find them. So I'm going to use a different color. Actually, let me not. So these guys are going to be pasted here. So let's just identify them just to make everything clear. So these guys, these guys, these guys, and these guys, right? Okay. And now, so that's step 2. I essentially just copy pasted all of the non-unit productions in G and put them in. So this is G prime and this is G in G prime. So now what's the next step? The next step is I take all of the unit productions. So in this case, I take all of the productions. S gives me A, S gives me C. And then in here, so in this production rule for S, I replace them with all of the non-unit productions that I can find. Okay. So what I mean by that is here I know that S gives me A, B, and C, right? So what I'm going to do is I'm just going to add all of the non-unit productions of A to C. So what that means is I'm going to take these guys and just place them in S as well. And then take this guy, so that's for B, and put it here. So this is for A, this is for B. And then I'm going to take the productions for C and put them in this guy here. Okay. So hopefully you're following me. Again, I'm going to do exactly the same procedure for A. So what does A give me? A gives me B, and it also gives me C, right? So I'm going to add the production rules, so the highlighted in yellow production rules for B. So in this case, this is B, and this is C, okay? And then again, I do the same thing for C. I know that C gives me B, so I get that C gives me the production rule for B, which in this case is just little b, okay? Okay, and now I've essentially created an equivalent grammar to G prime, where I've gotten rid of all my unit productions, because clearly you can see there are no pairs of variables. A gives you B, right? So so that's when you know that you've essentially accomplished or successfully finished the procedure. Okay, so just to make sure that everyone's still with me, let's just do a quick exercise. Again, I'll just give you maybe a minute to try it, and we'll look at the solution together. Okay, so hopefully that's enough time. You're going to see that this one actually isn't too long to do. So again, we're given this grammar G, and we want to convert it to an equivalent grammar G prime that has no unit productions. So remember, step 0 is, of course, you identify self-productions. In this case, there are none, so you can just check step 0. Step one is you identify all of the unit productions. So what are they? Well, in this case, I have S gives you S gives you B, and S gives you C. So those are the obvious ones. And after that, all of the other productions, so A, B, C, and D, all of them have terminals, right? So we know that they're not going to give you unit productions. So actually, it's quite nice here. The only unit productions that I have are S gives me B and S gives me C. Okay, so step two, just for the sake of sort of brevity, I'm not going to rewrite the whole grammar, but remember step two is you just copy the non-unit productions and paste them into G prime. So if I want to make this G prime, the unit productions, the productions I'm going to keep are going to be this guy, these guys, all of this, all of this, all of this, all of this, right? So that would be step two. Okay. And then finally, what's step three? Step three is I just, for each S gives me something, so for each unit production, I replace it by the right-hand side of my variable. So in this case, B, S gives me B. I know that B gives me capital A little a. So I can get rid of this and I can say that because I have the unit production B, I can give myself capital A little a. Okay. And again, the same thing for C. I can give myself the productions on the right hand side for C, which are going to be little c, capital D. So that's going to be C, CD. Okay. And that's it essentially. So this one was quite quick. That would be an equivalent grammar G prime. Yes, very good. I'm happy someone's following. This would be one equivalent grammar G prime that has no unit productions, right? So so hopefully that's hopefully that's clear. Again, if it's not, you can stop me. But if it is, the last component of simplification that we're going to look at is removing useless variables. So first of all, what is a useful variable? So a variable A in the set of variables V from a grammar G is said to be useful if it appears in at least one derivation. So that means that if you can find, so for instance, I start in S, and if you can find a derivation where you find some terminals A and then some terminals, and then you keep the derivation going, and then you get a string. So if these are, no, not sorry, sigma in the set of terminals, right? So if you can find a set of derivations, so a sequence of derivations, where a variable A, the variable A is in that sequence of derivations, then it's useful. Otherwise, the variable is useless. So in other words, how can a variable be useless? Well, either it can never produce a terminal string. So in other words, it's non-generating, or it cannot be reached starting from S. So it's unreachable. Okay. And then if we want to generalize this to a production rule X gives you Y is useless if it contains any useless variables either on the left or on the right. Okay. And so the idea behind, well, this isn't really a procedure. The idea behind useless variables and removing them is that, of course, if you remove any useless variables, your grammar doesn't lose any information. And so it's safe to remove the useless variables because you're going to preserve an equivalent grammar G, right? So it produces an equivalent grammar G prime if you remove all the useless productions. Okay, so that might still seem abstract to you, so that's why we're going to do an example. So imagine we have the following grammar G, where this is my grammar, and I want to get rid of all the useless production rules and useless variables. So wait, maybe actually let me answer that question first. Oh, that's a nice question. So why that's an interesting question. The question is why is there a useless variable in the grammar in the first place? That's a really good question. To be honest, if you're making a grammar yourself, it's very difficult to create a useless variable. So that I feel like that's your point, and you'd be right there. However, you can be given a grammar, and sometimes perhaps in some pre-processing step or some processing step, the sort of the processor kind of mistakenly forgot to, this is very far-fetched, but mistakenly forgot to remove a variable, or it was a lazy processor. So in that case, you ended up with a useless variable. That's a scenario. Another scenario is, you're in a test and you're given a grammar with some useless variables. That's another situation where it might occur. But I agree that in general, in practice, you only see useless variables when they're given to you. So that's a good question. Yes. Okay. So now let's try to remove these useless productions, which we wouldn't find anywhere else but in this example. So where are they going to be? Well, remember what's a useless a production, or what's a useless? Let's go with variable first. A useless variable is either a non-generating or unreachable. So for unreachability, there's actually a nice trick that you can use to very easily check if a variable is reachable or not. So you can just create a very simple graph, G, where there's a vertex for each variable. So in this case, how many variables? I have A, B, and C. And then I'm going to create an edge from S to, from a vertex to another vertex if there is a production rule that looks like, so for instance, I'm only going to put an edge, sorry, from S to A if I have something like S gives me something, A something. Okay, so that's pretty straightforward. And then once you do this, every vertex which isn't reachable from S is going to be an unreachable variable. Okay, so that's the trick. Instead of kind of just forcing your brain too much and trying to see if it is unreachable, this is a very simple procedure to check. So from S gives me AC. I know that there's going to be an edge from S to A and not to B, sorry, from S to C, right? Then there's a self loop on A, I don't really care about that. There's an edge from B to A, okay? And then there's an edge from C to A. So that's not, I can put it, but it's not that important. What's important really is to see that your vertex B here, or your variable B, is unreachable from S, right? So because it's unreachable, it makes it useless, right? It's unreachable because it can't be reached starting from your start variable S. Because it's unreachable, it's useless. And so because it's useless, I can just remove all of the production rules in my grammar G that have B on the left-hand side or on the right-hand side. So in this case, I'm going to just remove this guy because it has B on the left-hand side, okay? And that's the only one that's the only instance that has production rule instance that has B as a variable, okay? So that unreachability is the easier one to do. Non-generating is a bit trickier, but the idea is, non-generating is a bit trickier. The idea is if you can have a derivation that's going to lead to some string where you just have a string of terminals, then that variable is going to be generating. So let's check it for S, A, and C. So for S, how can I produce a terminal string? Well, I can say S gives me A, and then A gives me lambda, right? So this would be a generating a variable because there's at least one derivation rule that produces a string of terminals, okay? Again, the same thing for A. I can say A gives me lambda, so that would make it generating. However, for C, if I have C, the only production rule I can use is C gives me ACA, right? And then once I have that, well, I need to replace C with ACA again. So I'm going to get A, ACA, A. So it doesn't really matter what I do with these A's, right? Because for as long as I use this production rule, I'm always going to be stuck with the variable C. So I'm always going to be stuck with the variable C, meaning I'm never going to get a full string or a full sequence of terminal symbols, okay? So what that means is that C, the variable C, is non-generating, okay? It's non-generating because it can never produce a string of terminals. So that means I can remove any production rule that has C on the left-hand side or on the right-hand side. So in this case, I can eliminate this one, and I can eliminate this one. So the variable, the simplified grammar that I get, is going to be this grammar here. Okay, and you can see that it's equivalent because I've removed everything that's useless, so I haven't lost any information. Okay, so hopefully that's clear. If it's not, let's do a quick exercise. How am I doing on time? Not too great. So let's do maybe 30 seconds because I want to finish in time for an exercise. Yes, it is. Okay, so yeah, so I don't know if, yes, it is, meaning yes, it is recorded. So that's difficult. You can't really access it if you're in a different section because it's on the Moodle for Dr. Shiri's section. I don't really have time right now, but what I'm going to try to do is maybe later in the week, I'll try to post the ones from the previous weeks to my YouTube channel, so then everyone can access them in case they're in different sections. Okay, so that's, yes, no problem, I can do that. It's just I don't really have time right now, but I'll do it eventually. And if I don't, just send me an email to remind me. Okay. All right. So what's the, yes. Okay. So I have an exercise here where I want to eliminate all my useless productions. Okay. So again, a reminder, what's a useless production rule? What's a useless variable, sorry? Well, it's either going to be non-generating or it's going to be unreachable, right? So what are the unreachable variables? Well, let's look at our nice graph here. So I know S, so S can reach A, B, C, right? So S can reach A, B, and C. Can anything reach D? Well, A goes to B, so we don't really care about that. B goes to A. Oh, okay. C goes to D. Okay, so that means that if C goes to D, that means that they're all reachable, right? So there are no unreachable variables that I can delete, which sucks because that's always the easiest part. How about non-generating variables? So is S generating? Yes, because S can give you A, right? The single, so remember I'm looking for terminal strings. Is A generating? Yes, it can give you the lambda string, the empty string, sorry. Is B generating? Well, you can't see directly, but if I do B gives me AA, and then I replace A with lambda, then I can get the terminal string A. So all of these guys so far are generating. However, C here is not going to be generating. And the reason for that is because if I replace C with the production rule, the only production rule here that I have is C has to be replaced with CCD. I think that, is that exactly the same? Oh no, okay. C is going to be replaced with CCD, so that's going to be C, C, CD, and I'm going to get another D. So it doesn't really matter what these guys are. What you're going to notice is if you continue your derivation forever, you're always going to be stuck with something, C, something, right? So what that means is you can never produce a string of terminals, which means that C is non-generating. So I can remove this guy and all of the production rules with C on the right-hand side. So I can also remove this. And as someone pointed out, D, even though D gives you, well, in fact, D is actually generating, right? Because D can give you this string of terminals, okay? So it is generating. However, once you delete, so what you need to notice here is once you delete C, then you delete this edge, right? And so now what happens is D is not reachable from S because the sort of connection, the only connection from S to D was through C, but now that you've removed that, D is going to be all alone. And so what that means is D is now unreachable, so I can remove all the production rules with D, okay? So then the the simplified grammar I get, simplified grammar I get is going to be this. Okay, you see what I mean, this, okay? So that's going to be the simplified grammar, okay? So I hope that is clear, all right? So now let's put everything together. If you're given a grammar G and you want to completely simplify it, then what are you going to do? Well, the first thing you're going to do is you're going to remove the nullable variables and the lambda production rules. Second thing you're going to do is remove the unit productions. And the third thing you're going to do is remove the useless productions. And what's very, very, very important to know is this is, I wouldn't say the only, I'm not sure if it's the only order, but this is, well, actually, yes. So this is the only order that's going to 100% give you a simplified grammar at the end. So if you start with 2 and then do 1, you might not still have a fully simplified grammar. So what's important for you to remember is obviously how to simplify, how to do each of these, right? How to do each of these steps, but also the order of the steps is very important. Okay. So let's do, how much time do I have? Okay. So let me do the exercise. This exercise, I'll show you how to do it because we're running short on time. Okay. So I have the following grammar G here. So this is my grammar, and I want to simplify it. Okay. So remember, what are the? Well, I just showed you what are the steps to simplifying a grammar. Well, the first step is I'm going to want to remove all the lambda productions, right? So to do that, I need to identify all the lambda productions, right? So what are they going to be? Well, I know that A gives me lambda, right? And D gives me lambda, right? So that's a first pass. Then what else do I know? Well, I know that B gives me D and D gives me lambda. So B is also a nullable variable. And then C gives me B, right? C gives me B, which gives me D, which gives me lambda. So these guys are going to be the nullable variables or the variables that can produce empty strings, right? So now what I need to do is remember the step for removing lambda productions is I just copy paste all of the production rules that are not lambda productions and then replace all the production rules with nullable variables by all of the possible combinations of replacing or not replacing lambda. Okay, so what is that going to look like? Well, I'm going to remove this lambda and I'm going to remove this lambda and then I'm going to do all the possible combinations. So because for the sake of time, I'm not going to want to rewrite all of this, but I'm going to do it first for AAA. So what is that going to be? Well, I can replace capital A with lambda. So that would give me AA. So this would be for A gives me lambda. Then I can do the same thing for ABB. So I can replace one of the B's with lambda or both of the B's with lambda. So this would be for B gives me lambda. And then for DAB, I can do the same thing since D and B are both nullable variables. So I can get, I can replace D with lambda, so that would be AB. I can replace B with lambda, that would be DA. And I could replace both with lambda, so that would be A. So this would be for B gives me lambda and D gives me lambda. So now the only thing I'm going to do is I'm going to remove the duplicates that I have. So I'm going to remove AB and I'm going to remove A because duplicates don't give me anything extra. So it's fine if I remove them. Okay, and I'm going to do exactly the same thing for all the other production rules. So for AAA, I'm going to replace all the possible combinations. So AA, AA, I know I'm just saying the same thing, but hopefully you know what I mean. So this is for A gives you lambda. And then for this guy here, the only thing I can do is replace the capital B with lambda. So that's going to be B. This would be for B gives me lambda. Again, don't replace D with lambda because if you do that, you're going to add back a lambda production, which is not what you wanted. Okay, you didn't want to add back a lambda production. Okay, and so the same thing for C gives you B, don't add a lambda production, and then for D gives you BDA, then I'm going to do the same thing and get a BA. Okay, so that's step one, that's for removing lambda productions. For the second step, I'm going to want to do what? Remove unit productions, right? So what are the unit productions here? That's weird. Okay, so I have C gives me B, right? And I have B gives me D. So then I also have C gives me D, right? So these are the three possible pairs of unit productions. Okay, so again, the whole point is you're going to remove all of you're going to copy paste your grammar and then remove all the unit productions and then add back all of the production rules that come from these guys. So that's what I'm going to do. I'm going to remove this unit production rule and this unit production rule. Okay, and then I'm going to add what I'm going to do. Yes, so B, okay. So B, what I'm going to do is I'm going to add the production rules for D to B. So that's going to be, I'm going to add these guys to B. So I'm going to add BDA and BA, right? And then for C, I'm going to add the production rules for B and for D. Okay, so I'm going to add the production rules for B. So be careful not to recopy this. I'm only adding the original production rules for B, which is B, 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 and the original production rules for D, which is BDA, B. Okay. Yes. So you finish with unreachability and with non-generating. So that's where we're going to head to. But I like that you're ahead of the game. So 3, the last thing is you want to get rid of the useless variables. Okay, so someone pointed out that C was unreachable, and I think that I agree because let's first do non-generating. It's going to be easy to do non-generating because here I can have S gives me AA, so that one's generating. A gives me A, that's generating. B gives me B, that's generating. C gives me BA, that's generating, and D gives me BA, that's also generating. So there are none, right? There are no non-generating variables. However, there are a few unreachable variables. So what are they going to, there's exactly one actually, not a few. So you use the same sort of graph technique. If you start at S, where can you go? You can go to A, you can also go to B, you can also go to D, right? So now I'm left with C. Is there any way I can get to C? So why do you say that C is unreachable? Oh, I see why you say that. B, okay. Okay, so yeah, I had a small bug in my head. C is unreachable because if you start at S, so you know that you can go to A, B, or D. from A, you can only go back to yourself. From B, you can only go back to B or D, right? So that's fine. From D, you can only go to D. So there are no production rules that are going to lead to C, okay? So yes, indeed, they are unreachable. C is unreachable, so that means that after doing all this work, I can remove the production rules with C. So I can remove this, and that's going to be the only production rules, set of production rules with C, okay? D is reachable because if you're at S, you can go to D using, for instance, this one, okay? So it doesn't mean that, remember, I'm out of unit productions. I just mean that from S, I can go to D using any form of production, okay? All right, so, okay, so I am gonna go maybe a few extra minutes just because the next section isn't that long to explain, okay? So, but hopefully that's clear for simplifying a grammar. So let me just answer that question. Is it okay as a tool when you find a variable non?
I'm asking about the exercise that we just did before
Yes.
this one.
Yes.
If you could scroll to it, I could show you what I mean.
This exercise.
Yeah, the one before this one.
Oh, the one before.
Uh,
Yes.
yes. Yeah. So when we said that C was non-generating and then therefore D was non-reachable, is it okay to say that for every production, if we find a production, let's say C, that we said was non-generating, then any production that has C is also going to be either non-generating or unreachable, right?
So not exactly, no. If so, for instance, here, so that's a good question though. Here, for instance, I had B gives me, I don't know, BD, right?
Mhm.
Then even if I remove C, D is still going to be reachable, right? So I can still reach D from B. So I'm still going to keep this production rule. I'm just going to remove the one that has C with it.
Well, okay, I think I'm going to rephrase my question. I think it's only going to work if the first variable is unreachable, then any other variable that has that unreachable variable is going to be
Yes,
unreachable. Okay, but it's
yes,
not true for generating.
yes. So I think what you're talking about is like if you have S gives you like A, B, and then maybe you have C gives you D, E, then I mean C is unreachable, so of course D and E are going to be unreachable.
Exactly. Yeah,
Yes, yes, very good. Yes, yes, for sure. You can do that. Yeah,
thank you.
yeah, no problem. Okay, so okay, so as I was saying, I hope that's clear for simplifications. It looks like it is. So yes, I'm just going to quickly talk about normal forms, and we're going to do one quick example about them. So normal forms. So the idea behind normal forms is you're given a grammar, a G, and you're going to want to convert it to a specific kind of form, sorry, where the production rules have a specific sort of shape or also form. And the whole reason to do this is because you're going to see in the lecture that once you convert a grammar into a normal form, it becomes a lot easier to process, and it becomes a lot easier computationally. There are some things that you can't do with a non-normal form grammar that you can do with a normal form grammar. So I'm not going to get into the theoretical details, but just keep that in mind when you attend the lectures on normal forms. Okay, so there are two types of normal forms that we're going to look at in these in a very small span of time. The first one is known as Chomsky normal form. Chomsky normal form is essentially you're given a grammar G, and it's in normal form if all of the productions look like you have a variable on the left and then exactly two variables on the right, or you have a variable on the left and a single terminal string on the right, okay? So for instance, if I have S gives me AB, A gives me A, B gives me B. This is in Chomsky normal form, okay? However, if I look at this grammar here, I see that, yes, I have S gives me BC, but I have that S gives me a single variable. So this does not match the definition of Chomsky normal form. And then the same thing here, I have two terminal strings, so that's not going to work with this guy. And here I have, a terminal string and then a bunch of variables. That also doesn't work for CNF. Okay, so now that you know now that you hopefully kind of see what a grammar in Chomsky normal form is there a way to convert it? Is there a way to systematically convert a grammar that's not in CNF to a grammar that is in CNF? But yes, and it's actually quite easy to do. So the first step in converting a grammar G, so if you have a grammar G and you want to convert to G prime, the first step to do so is you want to simplify a G. Okay, so you're going to remove the lambda productions, remove the unit productions, remove the uses productions. So that's the whole reason why we did the simplification, was exactly for this, because if you want to get a grammar in CNF, you have to simplify it first. Okay. The second step that you're going to want to do is, for each terminal, X and T, you're going to want to create a production rule. T of X gives you X, okay? So clearly this doesn't conflict with the Chomsky normal form definition or form, because remember, the second production rule that could be allowed is a variable gives you a terminal. So we're going to add all those terminals, okay? And then if you have, for instance, the production rule A gives you, let me think of an example, A, B, BB, right? So let's say something like this. Then what you do is you convert these guys to their variables. So let's say TA, B, TB, B. And then what you're going to do is you're going to want to have only pairs of variables on the right-hand side. So you're going to essentially take this and call it variable 1. So then variable 1 is going to give you B, TBB. And then you're going to take this, call it variable 2, and make variable 2 give you TBB, so that now you can remove these two variables and get V2, and then remove these two variables and get V1. And now this is indeed in CNF, right? I mean, this sort of, this production rule has been converted to an equivalent a CNF form, okay? So again, that might still seem abstract, so we're going to do a quick example. So we have the following grammar G, and we want to convert it to a to Chomsky normal form. So of course, the first step would be to simplify, if this is G, simplify G. I'm not going to do that. I'm going to leave that as an exercise for you. I'm just going to directly give you the simplified form. That's going to be S gives you BS, S gives you AA, A, B, A, B. Okay, so somehow you should get this simplified grammar G, okay? So what's the second step? The second step is I'm going to add the sort of terminal productions. TA gives me A, and TB gives me B, right? Hopefully so far so good. The next thing I'm going to do, I'm going to replace everywhere I see terminals that are conflicting or violating the CNF, I'm going to replace them with variables. So for instance, TB, I'm just going to replace that with TB. AA, I'm going to replace the little a with TA. Here, I'm not going to touch anything, right? I don't want to introduce a variable TA, because then S gives me TA would not be in Chomsky normal form. Okay, so I'm just going to leave it as S gives me A, because that is in Chomsky normal form. Okay, that is the production rule is in Chomsky normal form, not the grammar. And then for little a, little b, I'm going to replace that with TA, TA, TB, and I'm going to do the same thing for A. Okay. And then the last step is I'm going to take all of the production rules where the right-hand side has more than two variables, and then use that kind of replacement, or the kind of adding a variable and then replacing or substituting it. So here there's only one such instance. Here I have TA, TA, TB. I'm just going to take the last two and say, well, this is going to be V1. So I'm going to add my production rule V1, gives me TA TB. So then I can, without sort of loss of generality, now replace TA TB with V1. And then here, I'm lucky I don't need to do the same thing again, because I can just replace V1. I can just replace TATB by, again, V1. And this, if you look carefully, is going to be in Chomsky normal form. Note that you're not necessarily decreasing or reducing the number of production rules. So in this case, I had 1, 2, 3, 4, 5, 6, 7. I had 7 production rules in the original grammar. And in this new grammar, I have 8. So I have 8 production rules. So it doesn't necessarily simplify and reduce and convert to CNF. Doesn't necessarily mean you're reducing the number of production rules. It just means that you're converting it to a form that's familiar. And in this case, that is in CNF. Okay. So I know I'm going a bit fast, but once you get the sort of rough idea, these examples become pretty straightforward to do. It's just, procedural. You apply the simplification, then you apply the, TA gives you A, and then you apply the replacements on all of the production rules. So this is usually pretty well done by students, okay? If it's not, of course, you can let me know. So that was one a normal form. The last thing, and the last normal form we're going to talk about quickly, actually, because it's not really discussed in depth in the lecture either, is known as the Greibach normal form. And a grammar in GNF, in Greibach normal form, is a grammar G where all of the production rules look like a variable on the left-hand side and then a single terminal plus 0 or more variables after the terminal. So for instance, I can have A gives me A BB, or A gives me A B C D, or just A gives me A. So these are all valid. Some examples of non-valid Greibach normal form production rules would be something like A gives you B. So this is not valid because there is no terminal string at the beginning, or something like A gives you B B A. So there is no terminal string after. There shouldn't be a terminal string after. And you can, there's an infinite number of production rules that won't work, but those are just a few. So for instance, here, S gives me this set of production rules. These two violate Greibach normal form because, for instance, in the first two cases, you have 2 terminal strings instead of a single one, which is a violation. However, this guy, if you have a single terminal on the right, then that's not a violation of Greibach normal form. That would be okay. So there isn't, strictly speaking, there isn't a procedure that we talk about. Well, at least when I took the course and since I've been TAing the course, there hasn't been a procedure presented to the class. There is one, of course, that exists, but there isn't a procedure presented to the class for converting a grammar to Greibach normal form. You just have to kind of know the what the form is, and if you're given a super simple example, maybe how you could convert it. So what's an example I could give you? If you have something like, I don't know, I can't think of anything off the top of my head. Well, if you have something like S gives you A, B, B, then you should be able to say, oh, well, I can just say TB gives me B, and then replace the B with the B here. And then that would be in, so I'm assuming B gives me A or something. And that would be in Greibach normal form, okay? But there's not going to be examples that are like super involved like this one. It's going to be mostly based off intuition. Okay, so yeah, so again, I always keep going over the time. I really apologize for that. But yeah, so that's it for this week's tutorial. As a professor, yeah, you're welcome, Ryan. has the professor? No, he has not talked to me about the midterm. What do you have any? Okay, all right, okay. Yes, all right. So okay, good. So yeah, if there are no other questions, wish you the best, and see you next week. Okay. All right. So there are no other questions. All right. Take care, everyone. Bye.